The strangest part of living on Earth is that almost nothing in daily life prepares the body for how fast the planet is actually moving. The floor under your feet seems fixed. The table seems fixed. Even a cup of water seems perfectly still. A cup of water seems fixed. Yet the surface of Earth is not fixed at all. Near the equator, the planet carries that surface eastward at about 1,040 miles per hour, or about 1,675 kilometers per hour, simply because Earth turns once every day. At the same time, the whole planet is circling the Sun at about 67,000 miles per hour, roughly 107,000 kilometers per hour. Those are not small motions hiding in the background. They are immense, continuous, and physically real. This is where feeling and physical reality begin to part ways. Human sensation gives the impression of rest, because sensation is not built to report every kind of motion equally. The body is very good at noticing a shove, a stumble, a sudden turn in a car, or the drop of an elevator. It is much less useful as an instrument for detecting motion that is broad, shared, and steady. That is not a flaw. It is a design fitted to survival on the scale of ordinary life. A nervous system that reacts to every smooth background motion as if it were a threat would be exhausting and unreliable. The body is tuned to changes that matter for balance, footing, and orientation. When a plane reaches cruising speed and the climb is over, the cabin often begins to feel almost ordinary. You still know the aircraft is moving, but the strong bodily sense of motion fades compared with takeoff, landing, or turbulence. The same thing happens on a smooth train. When the motion is steady and everything around you shares it, the body stops treating that motion as urgent information. Earth works in that same broad pattern, but on a far larger scale. The ground, the buildings, the air, and your own body are all being carried together. Because the motion is shared, there is no daily jolt announcing it. The mind interprets that shared motion as stillness. That interpretation feels convincing because nothing in the room is sliding away from anything else. The room is being carried as one system. The body is inside the system, not outside it, looking in. The key distinction is not speed alone, but whether that speed is changing. In physics, moving fast is not the same thing as being pushed around. A car at rest in a driveway and a car traveling smoothly on a highway can feel surprisingly similar to a passenger if the ride is steady. What stands out to the body is not speed by itself, but acceleration, deceleration, tilt, vibration, and other changes in motion. The vestibular system in the inner ear is especially important here. The semicircular canals respond to angular acceleration, while the otolith organs respond to linear acceleration and gravity. At constant velocity, the signal fades. That is why a smooth background motion can pass beneath awareness even when the actual speed is enormous. Earth's rotation is a powerful example of this principle because it is steady and shared. The planet does not spend the day jerking under us in bursts. It turns with remarkable regularity. NASA notes that the sidereal rotation period is about 23 hours, 56 minutes, and 4 seconds. And with Earth's equatorial circumference near 40,075 kilometers, that steady turning produces the familiar equatorial speed of about 1,675 kilometers per hour. Those numbers are large, but the turning is so smooth that human sensation does not register it as a daily event. In ordinary life, there is no repeating shove each morning to announce that the planet has started moving again. It never stopped. We were simply born into the motion and remain immersed in it. Not every place on Earth moves eastward at the same rotational speed. the equator moves fastest. As latitude increases, that speed falls by the cosine of latitude, and at the poles, it drops to zero because the turning there is around the axis itself. This matters because many people hear the famous 1,000 miles per hour figure and imagine that every place on Earth is moving that fast around the axis. It is not. A person in a mid-latitude city is moving more slowly from rotation than someone on the equator. But even that reduced speed is still much greater than anything felt in ordinary walking or driving. Once again, the point is not that Earth is barely moving. The point is that the body was never built to read steady planetary motion directly. It also helps to notice how much human intuition depends on comparison. If you stand on a sidewalk and a bus rushes past, you can feel and see relative motion because the bus changes its position against you very quickly. If two people sit quietly in the same moving aircraft, there is far less obvious relative motion between them. Earth is closer to the second case. You, your chair, your walls, your local atmosphere, and the objects around you all share nearly the same eastward rotational motion. Because they share it together, your senses are not supplied with the kind of contrast that would make the motion obvious. Human perception is extremely good at contrast. It is much less direct when everything moves together. Physics says Earth is moving. The senses ask, compared with what in this room? That gap between physical truth and local perception is the heart of the paradox. This is also why the phrase, "Earth feels motionless," is both understandable and misleading at the same time. It is understandable because from a local frame, daily life is organized around surfaces and objects that keep their positions relative to one another. It is misleading because the larger system is in constant motion. NASA's education materials point out that Earth's orbital motion around the Sun is about 67,000 miles per hour. That means even on a calm afternoon, with curtains still and the room apparently at rest, the planet is crossing space at a speed far beyond anything familiar in ordinary transportation. The senses do not report that directly because they were never meant to serve as cosmic detectors. They were shaped to keep a person upright, oriented, and responsive to changes that affect survival over seconds and meters, not to reveal orbital mechanics over days and millions of kilometers. For long stretches of human history, the feeling of stillness was taken as strong evidence that Earth itself did not move. That conclusion made sense at the level of direct experience. If the ground feels stable and the sky seems to swing overhead, a geocentric picture feels natural. The long scientific shift away from that instinct did not happen because human sensations suddenly improved. It happened because measurement, geometry, and repeated observation proved more trustworthy than immediate impression. This is one of the quiet strengths of science. It does not insult sensation. It places sensation in context. Your body is reporting local conditions honestly. It is just not reporting the full structure of the system you belong to. That is why the opening paradox matters so much. The fact that Earth feels still does not mean Earth is still. It means shared, smooth motion is easy to live inside without noticing. It means the human body reads changes in motion far more strongly than steady motion. It means that intuition can be accurate on the scale of a room while being incomplete on the scale of a planet. And it means a person can stand quietly on the ground, feeling nothing unusual at all, while participating in several layers of motion at once: the turn of Earth, the orbit around the Sun, and the broader motion of the solar system through the Milky Way. The stillness is not false in the narrow sense of lived experience. It is simply local. Once that is understood, the flaw no longer seems like proof that nothing is happening. It becomes evidence that motion can be shared so completely that it disappears into the background of ordinary life. If Earth feels so calm while moving this fast, then how fast is it truly carrying us right now through space? The unsettling part is not that Earth moves. It is how many layers of motion are happening at once, while an ordinary afternoon feels almost completely stable. A chair seems fixed, a sidewalk seems fixed, a glass of water on a desk seems fixed. But that stillness is only local. At Earth's equator, the surface is being carried eastward by the planet's rotation at roughly 1,040 miles per hour, about 1,675 kilometers per hour. Farther north or south, that rotational speed becomes smaller, but it never becomes zero unless you stand exactly at a pole. And that is only the first layer. Earth is also circling the Sun at roughly 67,000 miles per hour, about 107,000 kilometers per hour. Then the entire solar system, Sun and planets together, is orbiting the center of the Milky Way at roughly 450,000 miles per hour, about 720,000 kilometers per hour. NASA's older Star Child educational material gives a nearby value of 828,000 kilometers per hour, which shows that the exact number depends on the model and assumptions being used. But the main point does not change. Even when your room seems perfectly calm, you are already inside several enormous motions at once. That stack of speeds can sound abstract until the scales are placed next to things the body already understands. A fast commercial airplane cruises around 500 to 600 miles per hour. A rifle bullet may leave the barrel at around 1,000 to 2,000 miles per hour, depending on the cartridge. The rotational speed at Earth's equator is already in that range, though you do not feel it as a blast of wind because everything around you shares it. Earth's orbital speed around the Sun is more than 100 times faster than a jetliner. The solar system's motion around the Milky Way is faster still by another large factor. Put differently, the ground beneath a person in a tropical city is moving eastward faster than many aircraft, while the entire planet is moving around the Sun at a speed far beyond anything in ordinary transportation. These comparisons are not there to exaggerate. They simply translate large numbers into familiar experience. And once that translation is made, the usual feeling of stillness begins to look less like a fact about the universe and more like a limit of ordinary intuition. The numbers were always there. Human senses were simply never built to report them directly. The first speed to understand is Earth's own rotation, because it feels the most personal. The planet turns once in about 24 hours. More precisely, once every 23 hours, 56 minutes, and 4 seconds relative to the stars. Since Earth's equatorial circumference is close to 40,000 kilometers, a point on the equator has to travel that full distance in one rotation. That is where the familiar figure of roughly 1,040 miles per hour comes from. It is not a dramatic burst. It is geometry combined with time. And geometry immediately explains why latitude matters. Near the equator, you are tracing the largest circle around Earth's axis, so your rotational speed is highest. Move toward the poles, and that circle becomes smaller, so the speed drops. This is why someone in Ecuador is being carried eastward faster by Earth's spin than someone in Canada, even though both are turning with the same planet. The distinction matters because it shows that how fast is Earth moving never has only one answer. The answer depends on which motion you mean, and also on where you measure from. Motion in physics is always attached to a frame of reference. The next layer is Earth's orbit around the Sun, and this is where the numbers stop feeling merely large and start feeling almost unreasonable. NASA gives Earth's orbital speed as about 67,000 miles per hour. That means, in the time it takes to sip coffee, the planet has moved many miles along its path around the Sun. In 1 hour, it has traveled a distance comparable to crossing a large country. Over a full year, that same motion closes into one orbit because gravity continuously bends Earth's path inward, while Earth's forward motion keeps carrying it onward. This is why orbit is not a straight fall and not a straight escape. It is a curved balance. The quietness of ordinary life hides this because the whole system near Earth's surface shares the motion together. Trees are not being ripped backward. Houses are not leaning into orbital wind. The atmosphere is not left behind. Everything close to Earth is participating in the same solar journey. Once that is understood, the oddness becomes sharper. The absence of sensation is not evidence of low speed. It is evidence of shared motion inside a gravitationally bound system. A useful way to picture Earth's orbit is to imagine not a racetrack on a table, but a deep and continuous turn that never announces itself the way a car corner does. When a car takes a sharp bend, passengers feel the change because the direction shifts quickly over a short distance. Earth's orbital direction changes too, but the curve is so enormous and the motion so steady that the body does not interpret it as a daily event. The same logic explains why passengers on a smooth long-haul flight stop noticing forward speed once the plane reaches stable cruise. They may still hear engines and see the wing, but the body no longer reads the motion as urgent. Earth's orbit works with the same principle, only on a much larger and more regular scale. That is why the phrase "Earth is moving right now" can be physically precise and emotionally unconvincing at the same time. The physics is correct. Human sensation simply evolved for footsteps, slopes, and sudden changes, not for detecting a planet sliding through space in a near continuous curve. Then the scale widens again. The Sun is not sitting at the center of the universe with planets politely circling it. The Sun itself is traveling through the Milky Way, and the solar system comes along because it is gravitationally bound to the Sun. NASA states that our solar system moves around the center of the galaxy at about 450,000 miles per hour, around 720,000 kilometers per hour, and needs about 230 million years to complete one galactic orbit. Older NASA educational material gives a close value near 792,000 to 828,000 kilometers per hour, again showing that different references round somewhat differently. But all of them agree on the scale. The galactic motion is far faster than Earth's orbital motion around the Sun, and incomparably faster than anything the body experiences in daily travel. Human history, by contrast, occupies only a tiny segment of that galactic path. Since the solar system formed about 4.6 billion years ago, it has gone around the Milky Way only about 20 times. Civilizations rise and vanish in what is, on that larger track, almost no distance at all. That comparison does something important to the imagination. It replaces the familiar idea of a stable cosmic address with something closer to a moving convoy. Earth is not only spinning, it is not only orbiting, it is being carried by a star that is itself following a long galactic route through a spiral arm region of the Milky Way. NASA notes that the Sun is located in the Orion Spur, extending outward from the Sagittarius arm. So even the sky most people picture as a fixed backdrop is not fixed in any ordinary sense. The stars in our neighborhood are moving. The Sun is moving. The whole local system is moving around the galaxy. When people say they feel still, what they usually mean is that they feel still relative to nearby objects. That is a perfectly practical truth. But it is only a local truth, and once the galactic scale is added, local truth begins to look very small. There is another reason these numbers are hard to absorb. The mind tends to imagine motion as something that must leave a visible trace. In ordinary life, fast motion means blur, noise, drag, or impact. But large-scale cosmic motion often does not advertise itself that way because there is no universal background grid painted across space for the eye to compare against. On Earth, you can tell a train is moving by watching trees slide past. In orbit around the Sun, there are no nearby trees. In the galaxy, there are no fixed cosmic lampposts arranged for human convenience. This is why astronomy had to build its understanding from measurement rather than from direct bodily experience. The motion is real, but the clues come from geometry, orbital dynamics, Doppler shifts, and long-term observation, not from the same instincts that help someone cross a street. Science did not discover these speeds by trusting first impressions. It discovered them by learning where first impressions stop being enough. Once those layers are placed together, an ordinary afternoon changes character. A person standing in sunlight is being turned by Earth's spin, carried by Earth's orbit, and transported by the Sun's passage around the Milky Way all at once. The local scene remains calm because the motions are shared across the immediate environment. But calm is not the same thing as immobility. That distinction matters because it reshapes the title itself. Asking how fast Earth is moving right now is not really asking for one number. It is asking which piece of the larger motion you want to isolate from the rest, relative to your chair, perhaps almost zero. Relative to Earth's axis, maybe hundreds of miles per hour if you live away from the equator, or over 1,000 miles per hour if you live near it. Relative to the Sun, around 67,000 miles per hour. Relative to the center of the Milky Way, hundreds of thousands of miles per hour more. And beyond that, astronomers can even speak about the motion of the Milky Way itself through the larger universe, a reminder that each answer opens into a wider frame. These numbers matter because they change the way stillness has to be understood. We often treat stillness as the normal condition, and motion as the exception. On cosmic scales, the opposite is closer to the truth. Motion is the rule. The impression of stillness is what appears when many motions are shared so completely that nothing nearby breaks ranks with them. That is why the room seems calm while the planet runs its path. That is why the afternoon feels ordinary while the solar system sweeps through the galaxy. And that is why the next step cannot stop at speed alone, because the real puzzle is no longer how fast Earth moves, but why the body seems so unequipped to notice any of it at all. What makes this so hard to accept is that the number itself sounds like something a person should notice. Near Earth's equator, the surface is carried eastward at roughly 1,040 miles per hour, about 1,675 kilometers per hour, simply because the planet completes one rotation in about 23 hours, 56 minutes, and 4 seconds relative to the stars. On paper, that is an enormous speed. In daily life, it passes almost unnoticed. The floor does not seem to sweep beneath us. A chair does not seem to be rushing through the day. The air in a room does not feel like it is being dragged sideways. The body reports calm, while astronomy reports motion. Both reports are real, but they belong to different kinds of measurement. NASA's spaceflight basics note that Earth rotates daily and that a geosynchronous orbit matches a period of 23 hours, 56 minutes, and 4 seconds, the same sidereal timing that sets the scale for Earth's rotation. The reason we do not feel Earth rotate begins inside the head, not under the feet. Human beings do not carry an internal speedometer for absolute motion. What we do carry is a balance system, built to keep the eyes stable, the posture upright, and the body responsive to changes that matter for survival over short distances and short times. The vestibular system in the inner ear contributes to equilibrium, orientation, and the sensation of acceleration of the head, along with the reflexes that stabilize vision and posture. In other words, the system is designed to react to turning, tilting, speeding up, slowing down, and losing balance. It is not built to announce smooth, shared motion that remains steady over long periods. That distinction is the center of the whole puzzle. The body is not failing to notice a clear signal. The signal it is specialized to detect is different from the one people imagine. When a car pulls away from a stoplight, your body notices. When the driver brakes suddenly, your body notices again. When the car takes a sharp turn, you lean and feel it in your muscles, your eyes, and your inner ear. But if the road becomes smooth and the car settles into a steady highway speed, the raw feeling of motion fades. You still know the car is moving because you see the landscape pass outside, hear the engine, and remember how travel works. But the bodily sensation becomes much weaker than it was during the changes. Earth's rotation is closer to the steady cruising phase than to the shove at the start. The motion is broad, smooth, and shared by the ground, the buildings, the nearby air, and your own body. Since the changes that the balance system is best at detecting are small under those conditions, daily life feels stable, even while the planet continues turning. The structure of the inner ear makes this easier to understand. The vestibular apparatus includes the semicircular canals and the otolith organs. The semicircular canals are especially important for rotations of the head. Research reviews from the National Institutes of Health describe the receptors in the semicircular canals as sensing angular acceleration, with later mechanical and neural processing producing signals closely related to angular head velocity over normal physiological ranges of motion. That is a careful way of saying something simple. The system is most informative when motion changes, especially in the ranges relevant to natural head movement. It is not a device for reporting a huge cosmic rotation that remains almost constant from 1 hour to the next. The body notices the start of a spin much more readily than a spin that has become uniform and broadly shared. That is why a sudden swivel in a chair is obvious, while Earth's persistent rotation is not. There is also a problem of scale. Your vestibular system evolved for the movements of an animal body, not for the motions of a planet. A person turns the head, bends, stands, falls, or changes walking direction over seconds. Those are the movements the system is meant to track. Earth's rotation, by contrast, is extremely slow in angular terms. The linear speed at the equator is large, but the planet only turns once per day. That means the angular change from one moment to the next is tiny compared with the fast head turns and body movements that dominate human life. This is one reason the number 1,000 miles per hour can be misleading when it is heard without context. It is a large, linear speed spread over an enormous circle. The rotation is real, but the turning is not abrupt on the timescale of the body's balance organs. When people imagine that such a speed should feel violent, they are often importing the wrong comparison, something like a car or aircraft changing direction rapidly, instead of a vast rotating system changing direction very gradually. Think about standing in an airport moving walkway. If you step onto it smoothly and continue standing while everything around you on the walkway shares that motion, the sensation quickly settles. You are moving relative to the floor beside the walkway, but not much is changing relative to your own local surroundings. Now imagine that walkway were not a strip in a terminal, but an entire city, with the buildings, the air, and every object around you moving together. The sensation of motion would become even less obvious because there would be so little local contrast left. Earth's rotation works that way on a much larger scale. We are inside the moving system, not watching it from outside. Human perception is strong at spotting relative motion between nearby things. It is much weaker at detecting a shared background motion when the whole local environment participates in it. That is why the room seems still. Stillness here is not the absence of motion. It is the absence of local mismatch. This is also why people often notice rotation only when rotation changes. Amusement park rides are a good example. A ride that starts spinning, speeds up, changes direction, or stops abruptly produces an unmistakable bodily response. The inner ear, the eyes, and the muscles all have to adapt at once. That is a very different situation from Earth, whose daily rotation is steady enough that the relevant signals are not presenting themselves as urgent disturbances. Vestibular research describes central processing mechanisms that support compensatory responses during head motion, including what is called velocity storage. But even in that literature, the core lesson remains the same for everyday understanding. These systems are about the processing of motion cues in ways that stabilize vision and posture during natural movement, not about revealing an absolute cosmic state of rest or motion. The body tells you when balance may be at stake. It does not tell you whether your planet is circling quietly through space. Historical experience shows how convincing this bodily silence can be. For much of human history, the fact that the ground felt stable was taken as evidence that Earth did not move. That conclusion had a certain common sense behind it. If you do not feel rotation, and the sky appears to move overhead, then a stationary Earth seems reasonable. What changed was not the body. What changed was the quality of measurement. Astronomy, geometry, and later mechanics showed that sensation alone was not enough for planetary truth. This matters because it reminds us that our senses are practical tools, not final judges of cosmic structure. They are reliable within the range they were shaped for. They are incomplete outside it. Earth's rotation sits right in that gap, large enough to matter physically, smooth enough to evade ordinary feeling. The body does not merely fail to feel Earth's rotation because the spin is steady. It also fails to feel it because gravity, ground contact, and the surrounding atmosphere create a coherent local world. You are not a loose object skimming across a rotating surface. You are part of a gravitationally bound system in which nearby things largely keep their places relative to one another. The practical signals entering the nervous system are dominated by local posture, pressure, muscle feedback, head movement, and visual stability. All of those can remain calm while Earth rotates underneath the sky. So daily experience is not lying. It is reporting the state of the local frame you live inside. That frame is calm even though the larger planetary frame is in motion. NASA's Earth reference material emphasizes that our planet rotates daily and revolves annually, while even the stars are not truly fixed in the deeper sense. Human sensation simply does not present all those layers directly. So the answer is not that Earth rotates too slowly to matter, and not that our senses are defective. The answer is that human balance is built to detect the kinds of motion that threaten footing and orientation, especially changes in motion of the head and body. Earth's rotation is too broad, too steady, too shared, and too slow in angular terms to appear in daily life, the way a shove, a stumble, or a fall appears. That is why the planet can turn continuously while a room seems at rest. If the body is so selective about what it can detect, then what exactly is it built to sense? And why can it miss something as large as a moving planet? The more unsettling motion is not Earth's daily spin, but the longer path that almost never enters ordinary awareness at all. Earth is moving around the Sun at an average speed of about 107,182 kilometers per hour, about 67,000 miles per hour. NASA states that clearly, and the number is large enough to feel absurd when set beside daily life. A person can stand in a kitchen, watch steam rise from a cup, and hear almost nothing except a clock or a fan, while the entire planet is crossing space at a speed far beyond any aircraft. That contrast is the center of the difficulty. If the motion is real, and if the speed is so large, then why does life on the ground not feel like a continuous rush? The first step is to separate motion from changing motion. Human sensation is not built to report speed in the abstract. It is built to report the kinds of changes that affect posture, orientation, and survival. A shove is easy to feel. Braking is easy to feel. A turn in a car is easy to feel. But a smooth, shared motion is very different. A recent review in the National Library of Medicine notes that the vestibular system has inherent limits and cannot detect constant velocity linear motion. Another review explains that vestibular processing is tied to the functional demands of natural head movements and spatial orientation. Put simply, the body is far better at noticing that motion has changed than at announcing that a steady background motion continues. That difference is why Earth's orbit can be physically enormous and still pass through daily life with almost no direct bodily signal. Imagine riding in a car that has just entered a freeway. The moment of merging is obvious. The push into the seat is obvious. A lane change at high speed is obvious. But once the road straightens and the speed becomes stable, the raw feeling often fades. You still know the car is moving because signs pass, trees pass, and the road outside provides a reference. Now remove those roadside references. Put the car inside a perfectly smooth enclosed tunnel with no windows, no bumps, and no change in engine note. The sense of motion would become much weaker. Earth's orbit is closer to that second case. We do not sit outside the planet watching reference posts fly by. We live inside the moving system. The whole surface world, the oceans, the atmosphere close to us, and our own bodies share the same solar journey together. This is why the size of the speed can be misleading if it is heard in the wrong way. 67,000 miles per hour sounds like the kind of number that should tear hats off heads and bend trees flat. But orbital motion is not that kind of event. NASA's Parker Solar Probe material explains that anything launched from Earth already starts out moving at about the same 67,000 mile per hour sideways pace as Earth itself. That one sentence carries an important lesson. A rocket does not begin at zero with respect to the Sun. It begins already sharing Earth's orbital motion. The motion is inherited because Earth, everything on it, and everything launched from it begin inside the same moving frame. That is why the body feels no solar wind of orbital speed rushing through the streets. The streets are already part of the moving platform. The path around the Sun also needs to be pictured correctly. Many people hear that Earth is orbiting and imagine something like a race car forcing its way around a tight circular track. That picture creates the wrong expectation. Earth is indeed in continuous curved motion, but the curve is spread over an orbit whose full path is close to 970 million kilometers, according to JPL educational material. Over 1 year, that enormous path closes into a loop. Because the radius is so large, the change in direction from one moment to the next is extremely small on human scales. The body is not being whipped around a short bend. It is being carried through a vast, gradual turn that unfolds over months. The geometry matters because large speed does not automatically mean strong felt disturbance. A wide curve taken smoothly can feel calm, even when the actual speed is enormous. That wide curve still involves acceleration in the physics sense, and this is where people often get stuck. It is true that orbit is not identical to straight-line motion. Earth's direction is constantly changing as gravity bends its path toward the Sun, but the acceleration associated with that curve is steady, shared, and modest compared with many familiar changes of motion in daily transport. Using Earth's orbital speed and orbital radius gives a centripetal acceleration of about 6/1000ths of a meter per second squared, only a tiny fraction of the gravitational acceleration we feel every moment at Earth's surface. That does not mean the orbital motion is unimportant. It means its dynamical effect on the body is overwhelmed by the far stronger and more immediate signals of ordinary gravity, posture, pressure on the feet, muscle tension, and local head movement. A person is already living inside a much larger background force field, so the subtle, steady inward bend of Earth's solar orbit does not stand out the way a bus turn stands out. There is another reason daily life remains so calm. Earth carries its nearby environment with it. The atmosphere is not waiting in place while the solid planet slides underneath. The oceans are not being left behind on the orbital path. Gravity keeps Earth's surface, air, and water bound together as one system. JPL's educational material says plainly that gravity holds us tight to the surface of our planet, so we move with Earth and do not notice its rotation in everyday life. The same physical idea helps with orbit. The entire Earth system shares the sun-bound motion together. Since nearby things are not peeling away from one another at 67,000 miles per hour, the body is not given the kind of local mismatch that would produce an urgent sensation. Human perception depends heavily on contrasts. When the local world moves together, that contrast is missing. Suppose someone says that because Earth is moving around the Sun so quickly, an aeroplane should somehow behave strangely once it leaves the runway, as if the planet were slipping away underneath it in a cosmic rush. But the plane, its passengers, and the air it flies through all begin with the same inherited solar motion Earth already has. Flight happens within the Earth system, not outside it. This is why spacecraft going sunward face an unusual challenge. NASA explains that Parker Solar Probe had to shed much of Earth's sideways orbital speed to get close to the Sun. That mission did not reveal a hidden burst of motion newly appearing after launch. It revealed that Earth's orbital motion is already there before launch begins. Space engineers must calculate it. Human senses usually do not notice it. The idea of a moving Earth once seemed unreasonable, partly because the ground did not feel as if it were in motion. If Earth truly circled the Sun, many earlier thinkers expected some obvious bodily or atmospheric sign. What gradually changed that picture was not a new organ of sensation, but stronger evidence and better mechanics. Once orbital dynamics, telescopic observations, and the mathematics of motion matured, the silence of the senses stopped being decisive. It became one more example of a practical human system being reliable at one scale and incomplete at another. Science did not prove that sensation is worthless. It proved that sensation alone is too local to settle the structure of the solar system. The wording matters too. When people ask why Earth's motion is invisible, invisible does not mean there is no evidence. It means the evidence is not delivered in the form many people first expect. We do not feel Earth orbit in the way we feel an elevator begin to rise. But the orbital motion appears in the calendar, in the return of seasons, in the changing length of daylight, in the geometry of the sky, in spacecraft navigation, and in the measured speeds that engineers must account for whenever a mission leaves Earth. JPL notes that Earth takes about 365.2422 days to go around the Sun. That is not an abstract textbook number. It is part of the reason leap years exist. The orbital motion is present all the time, but it reveals itself through patterns and measurements rather than through a dramatic bodily sensation. There is a practical lesson hidden inside all this. Human beings often trust the body most when the body is calm. Calm feels like proof, but in orbital physics, calm often means something else. It means the motion is smooth enough, broad enough, and shared enough that local disturbances are minimal. An ordinary afternoon can therefore feel stable not because nothing is happening, but because so much is happening together. Earth's orbital speed is real. The sun-centered path is real. The steady curvature of that path is real. What is missing is not the motion itself, but the sort of abrupt local change our nervous system is tuned to notice first. So the answer is not that Earth's orbit is too small to matter, and not that the body is broken. The answer is that our senses are selective. They are tuned for balance, footing, and nearby change. Earth's orbit around the Sun is immense, but it is also shared by the whole local world and spread across a path so vast that the body does not experience it as a dramatic event. The missing piece is no longer the orbit alone, but the instrument we keep trusting most. If the body can live on a planet moving this fast and still report stability, then what exactly is the body built to sense, and where do its limits begin to show? The body is precise in many ways, but it does not directly register absolute speed. That is the point where everyday intuition begins to separate from physics. A person can notice a stumble on a stair, the start of an elevator ride, the push of a bus pulling away from a stop, or the sharp side force of a car taking a curve. But if motion becomes smooth and remains steady, the feeling often fades. This is not because the motion has vanished. It is because the balance system inside the body is tuned to detect change more strongly than steady travel itself. Medical references describe the vestibular system as the inner ear system that helps with balance, head orientation, and the sensation of acceleration, along with reflexes that stabilize the eyes and posture. In other words, the body is built to answer a practical survival problem. Has motion changed in a way that may affect balance? It is not built to answer a cosmic one. How fast am I moving through space right now? That difference matters because people often expect the wrong kind of sensation from planetary motion. When someone hears that Earth is rotating and orbiting at enormous speed, the mind naturally imagines some bodily sign that should go with such numbers. But large speed alone does not guarantee a strong feeling. What the nervous system registers most clearly is acceleration, tilt, and shifts in orientation. Statpearls notes that the vestibular system contributes to the sensation of head orientation and acceleration in any direction, while the otolith organs respond to linear acceleration and gravity, and the semicircular canals respond to rotational acceleration. That language sounds technical, but the practical message is simple. The body is excellent at detecting motion that changes. It is much less direct when motion is broad, shared, and steady. You feel the moment the car starts moving. You feel the brake. You feel the lane change. But once the car settles into a steady speed on a smooth road, the raw bodily sensation becomes much weaker. You still know the car is moving because of outside references, engine sound, and memory. But the body itself is no longer shouting the message. Remove the visual cues and the feeling becomes weaker still. That is very close to the Earth problem. We live inside the moving system, not outside it. The ground, the nearby air, the furniture, the walls, and our bodies all share that motion together. Since nearby things are not violently changing their position relative to one another, the balance system is given very little reason to raise an alarm. Deep inside each ear are semicircular canals and otolith organs. Cleveland Clinic describes these as structures that detect head movements and support balance. The semicircular canals are arranged to detect rotational head movements, while the otolith organs help detect linear acceleration and head position relative to gravity. Research reviews from the National Institutes of Health go further and describe the semicircular canals as detecting angular acceleration and the otolith organs as contributing to the estimation of tilt and inertial acceleration. That is why the body quickly notices a head turn, a stumble, or the beginning of a spin. These organs are reading changes in motion and orientation that matter immediately to vision and posture. They are not trying to measure some universal background speed. This also explains why the phrase constant speed needs care. In basic mechanics, constant velocity means both speed and direction remain unchanged. The vestibular system does not directly signal that kind of steady linear motion. One source in perceptual neuroscience states it very plainly. Vestibular organs do not respond to constant velocity. They respond to changes in velocity, which means acceleration. Even when the semicircular canals later provide signals related to head velocity over natural ranges, they do so because the system is processing motion changes through fluid movement, hair cell bending, and neural adaptation. So when a motion becomes uniform enough, the signal becomes far less prominent than it was at the start. That is why the body can live inside long stretches of smooth motion without producing a dramatic sense of travel. The body does not merely sense motion. It combines several streams of information at once: vestibular signals from the inner ear, vision, touch, muscle tension, and proprioception from joints and limbs. Statpearls describes the vestibular system as contributing to proprioception and equilibrium, and notes the vestibulo-ocular and vestibulospinal reflexes that help keep the eyes stable and the posture controlled. That means the experience of "I feel steady" is built from a coordinated local world. Feet press into the floor, muscles match the posture, the eyes see a room that is not sliding sideways. The head is not rapidly turning. All of those signals tell a practical local truth: balance is under control. None of them are designed to report the solar system's motion through the galaxy. That local truth is why our senses are trustworthy and incomplete at the same time. They are trustworthy because they solve the problems they evolved to solve. If a branch under your foot shifts, the body needs to know. If you lean too far, the body needs to know. If the head suddenly rotates, the eyes must compensate fast enough to keep the world visually stable. Those are urgent, everyday problems. The vestibular system was shaped around them. A review of vestibular anatomy and physiology emphasizes exactly this framework. These organs and neural pathways support accurate estimation of tilt, inertial acceleration, posture, and visual stabilization. So the body is not missing Earth's motion because it is clumsy. It is missing it because Earth's motion does not present itself in the form that the body specializes in detecting. During takeoff, many passengers feel the push clearly. During turbulence, they feel every shift. But once the aircraft reaches stable cruising flight, the sensation often settles down so completely that people read, eat, sleep, or forget about the speed for long stretches. They are still moving quickly, but the motion has become smooth enough and shared enough inside the cabin that the body is no longer reacting strongly to it. Earth does this on a much larger scale. It is not only that Earth moves, it is that your immediate environment moves with it. Human sensation is strongest when nearby things stop agreeing with one another. When everything close to you shares the same motion, the result feels like rest. The body's limits show up even more clearly in unusual environments. Vestibular disorders can cause dizziness, vertigo, imbalance, and false sensations of spinning or motion. Cleveland Clinic and Merck Manual both describe how disruption of the vestibular system can produce major problems with balance and orientation. That tells us something important by contrast. The balance system is not a grand detector of objective speed. It is a biological guidance system. When its signals are disturbed, the result is not a better awareness of cosmic motion. The result is confusion, nausea, and instability. Its job is to keep a human being coordinated inside a local environment. Judged by that standard, it performs remarkably well. Judged as a detector of Earth's orbit or galactic motion, it was never intended for the task. The body does not feel kilometers per hour directly. It feels forces, changes, pressures, orientation shifts, and the consequences of acceleration for balance. That is why a sudden stop in a bus is memorable, while hours of smooth travel can become almost forgettable. It is also why the body can remain calm on a rotating, orbiting planet. Earth's motion is shared by the environment around us, and the relevant changes on the timescale of the vestibular system are small compared with the ordinary signals of posture and gravity. The body is not withholding information. It is reporting the category of information it is built to report. The body is built for balance and survival, not for measuring planetary motion. It is meant to keep you upright, not to settle the structure of the universe. That is why people once found a motionless Earth so plausible. The ground felt stable, and the body gave no sign of planetary travel. Only careful observation and measurement revealed that the body's calm was a local fact, not a cosmic one. The same lesson still applies. Sensation is reliable within its domain, but it does not outrank astronomy, dynamics, or measurement when the scale becomes planetary. The body tells you whether your footing is safe. Science tells you whether your world is moving. Gravity itself is always present as a dominant background input. The otolith organs help detect linear acceleration and also contribute to sensing head position relative to gravity. That means the body is constantly working inside a strong local gravitational field while standing, walking, bending, or turning. Against that background, the much subtler, steady effects of Earth's broader motions do not stand out in the same urgent way. The immediate job of the nervous system is to keep posture organized against gravity and movement in the local environment. Once again, the system is solving the problem nearest to the body, not the problem largest in the universe. So the answer is not that human senses are weak. The answer is that they are specialized. They are tuned for acceleration, tilt, balance, and local change. They are deeply trustworthy for walking, turning, climbing stairs, riding vehicles, and staying upright in a world full of sudden shifts. But they are incomplete for understanding motion on the scale of planets and stars. That is why Earth can rotate, orbit, and travel through the galaxy while daily life feels stable. If Earth is moving this way, and if we move with it, then why does the atmosphere not seem to fall behind? At first glance, the objection sounds almost impossible to answer. If Earth is rotating, And if the whole planet is also moving around the Sun at about 67,000 miles per hour, then why is the air not left behind, like smoke trailing from a moving truck? Why do we not wake each morning to a permanent westward hurricane produced by the planet, racing east beneath a mostly stationary sky? The reason this objection feels powerful is that it borrows intuition from ordinary life. In daily experience, when one thing moves through a fluid, the fluid often appears to lag, swirl, or get pushed aside. A hand moving through water leaves turbulence. A car moving down a road meets air resistance, so it seems natural to imagine Earth doing something similar as it spins and travels. But that picture quietly assumes the atmosphere was sitting still first, as if Earth was slipping through it like a rock through a pond. That is not how Earth and its atmosphere are arranged. The atmosphere is part of the Earth system. Gravity holds it close. Rotation shapes its motion, and from the beginning, it shares the planet's movement. Noah's material on the Coriolis effect makes that clear in a practical way. Because Earth rotates, moving air is deflected in ways that reveal the atmosphere is already participating in the rotating frame, not remaining fixed while the planet slides underneath it. The most direct physical reason is gravity. Earth's atmosphere does not hover in space as a detached shell. It is gravitationally bound to the planet, just as the oceans are bound to the planet, and just as you are bound to the planet when you stand on the ground. That does not mean every parcel of air is frozen in place. Air moves constantly. Winds blow, storms rotate, and pressure differences drive circulation across the globe. But all of that motion takes place within a system that Earth's gravity holds close. The atmosphere did not need to be newly dragged into motion each morning when Earth began to rotate. It has been part of the rotating Earth system for billions of years. The same inertia that helps explain why we do not feel Earth's motion also helps explain why the atmosphere does not fall behind. Britannica summarizes the core principle in a compact way. Since we are already in motion together with Earth, Earth appears still to us. The same logic applies to the air. It already possesses Earth's eastward motion because it formed, evolved, and continues to exist within Earth's gravitational influence and rotating frame. The atmosphere is not an external blanket that Earth is trying to outrun. It is one of the planet's own moving layers. An everyday comparison is a covered bowl of water resting on a turntable. If the turntable has been rotating steadily for a long time, the water does not remain motionless while the bowl spins underneath it. Friction and long-term coupling bring the water into the shared motion of the bowl, though currents and sloshing can still happen inside. Earth and its atmosphere are more complex than that, because air is compressible, heated unevenly, and constantly stirred by sunlight, terrain, and oceans. But the broad lesson survives. A system that has long been coupled does not behave like a stationary medium suddenly surprised by a moving object. The atmosphere has been rotating with Earth for immense spans of time. That is why the common mental picture of Earth moving under the air is backwards. A more accurate picture is air moving with Earth, while also circulating within that moving system. Noah's jet stream material gives a concrete example of this shared motion when it explains that air moving poleward retains its eastward momentum, while the Earth beneath has different rotational velocity at different latitudes. That statement only makes sense because the air already began with Earth's rotation. The interesting effects come from differences within the moving system, not from the entire atmosphere being abandoned in space. This is where latitude becomes important. Different parts of Earth's surface move eastward at different rotational speeds. Near the equator, the surface moves fastest because it traces the largest circle around Earth's axis. Closer to the poles, that eastward speed is smaller. Noah's explanation of the Coriolis effect says the cause is simple. Different parts of Earth move at different speeds. That detail helps explain many large-scale wind patterns. Air that moves north or south tends to retain some of the eastward momentum it had where it started, so its path bends relative to the surface below. This is why trade winds, westerlies, and jet streams do not move in simple straight lines from hot regions to cold regions. If the atmosphere were being left behind by a rotating Earth, the pattern would look far more violent and uniform. Instead, what we observe is something more structured and more revealing. The atmosphere rotates with Earth overall, while regional winds arise from heating differences, pressure gradients, and the conservation of momentum within that rotating frame. Noah and Euclid both explain that without Earth's rotation, the circulation would be much simpler. But because Earth rotates, air paths curve, and the global circulation breaks into more complex cells. That is not evidence of an atmosphere left behind. It is evidence of an atmosphere deeply embedded in Earth's motion. Another way to test the idea is to imagine what the world would look like if the atmosphere really did lag far behind. The result would not be subtle. There would be an almost continuous global wind of extraordinary speed relative to the surface. Trees, buildings, ocean waves, aircraft, and weather systems would all behave in radically different ways. The surface of Earth would be under relentless aerodynamic stress. That is not what we measure. Instead, real winds usually range from calm to storm strength, for reasons tied to pressure differences, temperature contrasts, topography, and rotation-driven deflection. Noah's educational material on weather systems and global atmospheric circulation shows that winds arise because the sun heats Earth unevenly, which creates pressure differences, and then Earth's rotation bends those flows into recognizable patterns. The atmosphere behaves like a fluid layer with its own internal dynamics, not like a stationary shell being peeled away by planetary motion. The absence of a permanent supersonic westward gale is not a missing mystery. It is exactly what physics predicts once gravity, inertia, and long-term coupling are taken seriously. A plane on a runway already shares Earth's eastward rotational motion before it even takes off. The surrounding air shares that motion too. Once airborne, the aircraft is still moving within the same rotating atmosphere, not outside it. That is why a plane does not need to fight a hidden 1,000 mph westward stream simply because Earth spins. What matters operationally are local winds, jet streams, and weather, not the false idea that the ground is racing under a mostly stationary sky. Air moving to different latitudes keeps some of its original eastward momentum, which is one reason jet streams exist and why their flow is shaped the way it is. So aviation actually confirms the deeper point. Pilots deal with relative motions inside the atmosphere, not with the atmosphere being left behind by Earth itself. The same reasoning explains why a helicopter hovering above one spot does not suddenly watch the landscape race away eastward beneath it. The helicopter, the air, and the ground all began with nearly the same rotational motion. Hovering is not stepping outside Earth's moving frame, it is remaining inside it. The history of the idea is also worth holding on to because it shows why this objection keeps returning. Before inertia and rotating frames were well understood, it seemed reasonable to think that a moving Earth should leave obvious atmospheric evidence. If the planet spun, why did clouds not all sweep in one overwhelming direction? If Earth orbited the sun, why did loose things not get stripped away? These older objections had force because they came from the same source as many modern objections: direct bodily intuition. But once Newtonian mechanics and later atmospheric science matured, the picture changed. Earth's gravity explains why the atmosphere remains bound. Inertia explains why air already shares Earth's motion, rather than needing to be continually pulled along from rest. Rotating frame effects explain why moving air bends and forms circulation patterns instead of tracing simple north-south paths. This is one of those places where science did not replace common sense with something alien. It refined common sense by widening the frame until the pieces stopped contradicting one another. There is one more detail that makes the atmosphere's behavior feel less mysterious. Earth's motion through space is not like a speedboat slicing through still water, because there is no preferred stationary background medium filling the solar system that the atmosphere must be left behind in. The old idea of a universal ether failed precisely because nature did not reveal such a medium in the way people expected. For Earth's atmosphere, the relevant physics is local and gravitational. The atmosphere is bound to Earth. Earth rotates. Air within that rotating system circulates because of heating, cooling, pressure gradients, and momentum conservation. Once the problem is framed correctly, the strange part is no longer that the atmosphere stays with Earth. The strange part is that it ever seemed more natural to imagine it doing otherwise. The air above your head is not resisting Earth's motion from the outside. It is one layer of the moving world you already belong to. So the answer is not that the atmosphere somehow ignores Earth's motion, and not that Earth secretly stands still after all. The atmosphere stays with Earth because Earth's gravity holds it, because the air already shares Earth's inherited motion, and because the winds we actually observe are differences within that moving system rather than evidence of a total lag behind the planet. That is why the sky above a city can look ordinary while the whole Earth turns. That is why weather maps show curved wind patterns instead of a single, endless westward blast. And that is why the next objection becomes even more interesting, because once the air is understood to move with Earth, attention shifts downward to the surface itself. If the planet turns this quickly, why does that spin not throw us off into space? The number sounds dangerous before the physics does. Near the equator, Earth's surface is carried eastward at about 1,040 miles per hour, around 1,675 kilometers per hour. A speed like that seems as if it should fling oceans out of their basins, tear the atmosphere loose, and make standing on the ground feel unstable. But that picture mixes together two very different ideas: moving fast and being weakly held. Earth does move fast. What changes everything is that Earth also holds very strongly. The pull downward from gravity is far larger than the outward effect associated with Earth's rotation, so the spin is real, but it is nowhere near strong enough to overcome the planet's grip on water, air, buildings, or human bodies. NASA's educational material notes the equatorial rotational speed, while NOAA's geodesy material explains that the effective gravity we experience near Earth's surface reflects Earth's attraction together with the centrifugal effect of Earth's rotation. A way to start is with the difference between gravity and the outward effect people usually have in mind. Gravity pulls matter toward Earth's center. Rotation introduces a much smaller outward tendency in a rotating frame, strongest at the equator and weaker toward the poles. NASA's Frames of Reference lesson states it directly. At the equator, the centrifugal force opposes gravity and makes the effective value of g slightly smaller there. NOAA makes the same point in geodetic language, noting that what we call gravity near Earth's surface is the combined effect of gravitation and the centrifugal fictitious force due to Earth's rotation. So the outward effect is not zero. It is just small compared with the main downward pull. That size difference is the center of the answer. Earth's ordinary surface gravity is about 9.8 meters per second squared. The outward rotational effect at the equator is only about 0.034 meters per second squared, using Earth's equatorial speed and radius. That means the outward effect is only a few tenths of 1% of surface gravity. In plain terms, rotation slightly lightens you at the equator, but only by a tiny amount. It does not come close to cancelling gravity. That is why people are not being thrown off Earth in any ordinary sense. The balance is nowhere near close. Gravity is winning by a huge margin all the time. This is easier to picture with a simple comparison. Imagine a child on a fast merry-go-round. If the rotation is strong enough and the grip is weak enough, the child feels pulled outward and may have trouble holding on. Now change the setup completely. Imagine the same child pressed to the ground by a force vastly stronger than the outward effect of the rotation. The spin still exists, but it no longer dominates the experience. Earth is like the second case. The planet does rotate, and that rotation does produce an outward effect, but gravity is so much stronger that the result is not panic or instability. It is a world where the outward term is present mainly as a small correction, not as the main story. Noah's materials even note that Earth is slightly wider at the equator, because long-term rotation has helped produce an equatorial bulge. That shows the rotational effect is real, but it also shows its scale properly. It reshapes the planet a little over geologic time. It does not eject the surface into space. That bulge matters because it proves two things at once. First, Earth's spin is physically significant enough to leave a measurable signature on the planet's shape. Noah notes that Earth is pudgier at the equator because of the centrifugal force created by constant rotation. Second, the fact that the result is only a bulge, not a breakup, tells you how dominant gravity remains. If the outward rotational effect were comparable to gravity, Earth would not merely be slightly wider around the middle. Its surface would be far more unstable. Its oceans would behave very differently, and the entire structure of the planet would be under severe stress. Instead, Earth is an oblate spheroid, not a shattered one. Rotation matters, but gravity sets the terms. The location on Earth also matters. The outward rotational effect is strongest at the equator because that is where the surface is moving fastest around the axis and where the direction of the outward effect most directly opposes gravity. Move toward the poles, and that effect becomes smaller. NASA's lesson explains that away from the equator, the centrifugal force reduces gravity by a lesser amount than it does at the equator. At the poles, the rotational speed around Earth's axis is essentially zero, so this outward correction disappears. This means a person at the equator is, in a strict physical sense, slightly lighter than a person at the poles, both because of Earth's shape and because of rotation. But slightly is the important word. It is measurable, with good instruments. It is not the sort of difference that makes daily life unstable. A familiar scale helps here. People often hear 1,000 miles per hour and compare it with a jet, a race car, or a machine shaking itself apart. But Earth's rotation is not a vehicle suddenly trying to corner on a short track. It is one full turn in roughly 24 hours, across a planet more than 12,000 kilometers wide. The linear speed sounds dramatic because the circle is enormous. The angular turning, spread across a whole day, is much gentler than people instinctively imagine. That is why the body does not feel the spin as a violent event, and it is also why the outward effect from that spin is modest. The number is large, but the geometry matters just as much as the speed. NASA's rotating frame lesson and NOAA's geodesy definitions together make that clear. The rotation contributes to effective gravity, but only as a small correction, not a reversal. The oceans give another strong reality check. If Earth's spin were close to overpowering gravity, the oceans would tell the story immediately. Water responds to forces efficiently. It redistributes, levels itself, and reveals imbalances quickly on planetary scales. Instead of flying free, the oceans remain bound to Earth and settle into the shape allowed by Earth's gravity field plus rotation. NOAA's geodesy materials describe the geoid as the surface the oceans would take under the combined effect of Earth's mass attraction and the centrifugal force of Earth's rotation. That is a precise scientific way of saying the seas already encode the balance between these two influences. And what that balance produces is a stable global ocean with a slightly equatorial bias in shape, not water escaping into space. The atmosphere tells the same story from above. Air is lighter and more mobile than rock or water, so if Earth's rotation were truly trying to throw things off the planet, the atmosphere would be one of the first layers to show it dramatically. But as already seen, the atmosphere remains gravitationally bound and rotates with Earth overall. Winds arise from pressure differences, heating, and momentum patterns inside that rotating system, not from the entire atmosphere nearly breaking free. The fact that the sky is not being stripped away by Earth's spin is another everyday sign that gravity is not barely holding on. It is holding decisively. The rotational effect modifies the system. It does not dominate it. The same logic applies to a person standing still on the ground. Your body is not performing a daily battle against being flung into space. The downward pull from Earth is enormous, compared with the small, upward-outward correction from rotation. The normal force from the ground supports you. Your muscles and balance systems organize posture, and the result feels ordinary, because it is ordinary under these conditions. In fact, if Earth rotated much faster, the story would change in ways science can estimate. The equator would lighten more. The bulge would grow. Weather and ocean circulation would be altered. Push the rotation far enough, and surface stability would eventually be threatened. But that is not the Earth we live on. The real Earth spins slowly enough in this mechanical sense that gravity remains overwhelmingly in charge. NASA's "What if Earth rotated in only 10 hours?" Material exists because changing the rate would matter. Our current rate does not come remotely close to unbinding the surface. History also makes this easier to trust. People once expected that a moving Earth should create obvious dramatic effects. If Earth spun, why were we not hurled away? Why were the oceans not swept off? Why did objects fall downward instead of backward? Those objections were reasonable before Newtonian mechanics and geodesy clarified how strong Earth's gravity is and how small the rotational correction is by comparison. Modern geodesy treats this quantitatively, not as a matter of impression. Earth's spin does pull slightly against gravity, especially at the equator. That effect is real enough to make Earth wider around the middle and to make effective gravity a little smaller there than at the poles. But the effect is tiny compared with a planet's gravitational hold. Gravity keeps oceans in their basins, air wrapped around the planet, cities anchored to the crust, and people firmly on the ground. Earth's rotation is not a reason for alarm. Why can't a plane just hover in place? It sounds like a simple trap for the idea of a rotating Earth. If the planet turns eastward, then why can a plane not rise, stop over one point, and wait while the ground moves underneath it? At first hearing, the thought feels practical. It uses an ordinary image, one thing moving below another. But the image leaves out the most important part. The plane does not begin from rest relative to space. It begins already sharing Earth's eastward motion, just as the runway, the passengers, and the surrounding air do. NASA's Earth orbit material notes that launch sites can use Earth's rotation as a boost, which only makes sense because anything sitting on Earth already has that rotational momentum before it ever leaves the ground. A useful way to see the mistake is to picture a smooth train instead of a planet. If you jump straight up inside a steadily moving train car, you do not slam into the back wall. You land close to where you started, because you, the floor, and the air in the car were all moving together before the jump. The same logic applies on Earth, only on a much larger scale. Earth's motion is not apparent, because the surface and everything on and around it are in motion together, and therefore seem at rest relative to one another. A plane lifting off from a runway is not stepping outside Earth's motion. It is continuing inside a moving system that it already shares. Inertia means an object tends to keep the motion it already has, unless a force changes that motion. Before takeoff, an aeroplane on the runway near the equator is already moving east with Earth's rotation. After takeoff, it still has that eastward motion. There is no reason for it to suddenly lose that inherited speed the moment the wheels leave the ground. The same is true for a helicopter in a hover. Hovering does not erase horizontal momentum. It only means the aircraft is maintaining its position relative to the air and surface below, as long as the local winds and pilot inputs allow. Earth's motion is already built into the starting conditions. The air matters just as much as the aircraft. Flight happens through air, not against empty space. FAA material explains that lift is generated by the motion of the airplane through the air, and that an aircraft's motion depends on the balance of lift, weight, thrust, and drag. NASA's Glenn Research Center says the same in slightly different language. The motion of the airplane through the air depends on the relative strength and direction of those forces, and if the forces are balanced, the aircraft cruises at constant velocity. So the pilot is not trying to hold still relative to the universe. The pilot is flying relative to the surrounding air mass. That is why the question, "Why doesn't Earth rotate under the plane?" quietly uses the wrong reference frame. The real frame for ordinary flight is the moving atmosphere above the surface. The FAA's helicopter handbook states that movement of an airfoil through the air creates relative wind, and the FAA's flight instruments handbook adds that wind moving across an airfoil at 20 knots is physically the same for the wing as the aircraft moving through calm air at 20 knots. That is a deep clue hiding in a simple flight lesson. Wings care about motion relative to the air. They do not care whether a philosopher would call the aircraft really still in some larger cosmic sense. A plane can only hover or cruise within the atmosphere by responding to airflow, not by stepping outside Earth's rotation. That is why helicopters seem, at first, like a stronger objection than aeroplanes. A jet normally keeps moving forward, so someone can say the jet is going with the flow, but a helicopter can hang over one spot, so it looks like a better test. FAA guidance on helicopter performance explains that hovering and climb are strongly affected by wind direction and velocity, and that translational lift occurs whenever there is relative airflow over the rotor disc, whether that airflow comes from helicopter motion or from the wind. In other words, even a hover is not a magical escape from moving air. It is an aerodynamic condition maintained inside an already moving atmosphere. If the air mass itself is moving with Earth, the helicopter moves with that system unless wind carries it elsewhere or the pilot corrects for drift. Imagine a plane parked at an airport in Florida. Before takeoff, it already shares Earth's eastward rotational motion, which is substantial at that latitude. The air above the runway shares that broad motion too, because the atmosphere is part of Earth's rotating system. When the plane lifts off, it does not suddenly become a neutral object suspended outside the system. It keeps the momentum it had at takeoff and continues moving through the local air mass. From the pilot's point of view, the operational problem is not, will the planet outrun me? But what are my airspeed, attitude, wind, and ground track? The existence of winds sometimes confuses the picture because winds really can move an aircraft relative to the ground. But that is not Earth rotating under a plane in the way the common objection imagines. It is an aircraft moving within different air currents inside the atmosphere. The atmosphere already participates in Earth's rotation, and then winds develop within that rotating system. So a plane may drift because of real winds, but not because the ground has suddenly begun slipping beneath a motionless aircraft. This is also why flight planning uses both airspeed and ground speed. Airspeed tells the pilot how the aircraft is moving through the air. Ground speed tells how fast it is moving over Earth's surface. A strong headwind lowers ground speed. A tailwind raises it. If Earth were truly rotating underneath a nearly detached atmosphere, the discrepancy would be dominated by that huge planetary motion all the time. That is not what pilots see. What they see are the effects of weather, local winds, and larger circulation patterns, all superimposed on an atmosphere that already shares Earth's broader motion. Spaceflight gives the clearest proof because rockets cannot ignore Earth's inherited motion either. NASA's orbit catalog states that satellites launched into low-inclination orbits can get an energy boost from Earth's rotation, especially from sites near the equator. High-inclination and polar launches receive less of that benefit because they do not make as much use of Earth's eastward momentum. That is not just a detail for engineers. It reveals the starting condition for everything that leaves the ground. Aircraft do not receive enough altitude or freedom from drag to turn this into an orbital effect, but they still begin with the same inherited momentum. To hover in place always means hover in place relative to something. For a helicopter pilot, that usually means relative to the ground below. But holding a hover over one point requires constant corrections because the air is rarely perfectly still. Even without invoking Earth's rotation at all, a helicopter will drift if the surrounding air drifts. So the everyday reality of hovering is already relational and active. The pilot is not finding a special point of absolute rest. The pilot is continuously managing a position inside a moving fluid system. A stronger version of the question sometimes says, what if the plane went straight up and shut everything off? Even then, the same principle remains. The aircraft would still retain the horizontal momentum it had at the moment of ascent, just as a ball tossed upward from a moving vehicle retains the vehicle's horizontal speed for a time. Over longer periods, drag, turbulence, and changing winds would matter, but none of that would turn the aircraft into an object suddenly left behind by Earth. The same mechanics that make Earth's motion hard to feel also make it hard to opt out of in ordinary flight. Shared motion remains shared, unless a force changes it. A plane cannot simply hover and let Earth rotate under it, because the plane, the passengers, and the air around it already begin with Earth's eastward motion. Flight takes place inside a rotating, moving atmosphere, not from some detached platform outside the planet's system. Pilots work with airspeed, lift, drag, thrust, wind, and ground track, because those are the real variables that govern flight. Earth's rotation is present in the background, and in some contexts, such as launch energy and large-scale atmospheric circulation, it matters a great deal. But it does not create the everyday effect of the ground racing away beneath a hovering aircraft. For most of daily life, the body reports stability. The floor feels steady. The air does not seem to be racing past. The sky appears to move overhead, far more obviously than the ground appears to move beneath us. If direct feeling were the only test, a motionless Earth would seem easier to believe. But science became powerful precisely because it learned how to ask a better question. Not, what does the body feel? But what physical traces would Earth's motion leave behind if the motion were real? Earth's motion is not something we merely infer from abstract equations. It leaves visible, repeatable marks in the behavior of pendulums, winds, ocean currents, and many other systems. Two of the clearest are the Foucault pendulum and the Coriolis effect. The Foucault pendulum is one of the most elegant demonstrations ever built because it turns Earth's rotation into something a person can watch with the eyes. In 1851, Léon Foucault introduced the pendulum as a direct demonstration of Earth's axial rotation. The basic setup is simple. The heavy bob hangs from a long wire and is allowed to swing freely. What makes it remarkable is that the pendulum's swing plane tends to remain fixed in space while Earth rotates beneath it. The Smithsonian explains the core idea clearly. If such a pendulum were suspended exactly above the North Pole, Earth would rotate once every 24 hours underneath it. So an observer would see the line of swing slowly change direction over the day. The pendulum is not being mysteriously pushed around by some hidden motor. The point is almost the opposite. Because of inertia, its swing direction resists changing, while the rotating Earth carries the floor beneath it. That detail matters because the pendulum is not proving Earth moves by storytelling or interpretation alone. It is showing a stable mechanical behavior against a rotating reference frame. In a museum, the floor, the building, and the visitors are all attached to Earth. The pendulum's motion, however, does not simply lock itself to the floor. Over time, the swing line appears to rotate relative to the room. The Smithsonian notes that this is especially easy to see when the pendulum is arranged to knock down pegs in a ring as the direction gradually changes. That visible change is the point. If Earth were not rotating, the room would not steadily shift beneath the swing plane in that way. The latitude dependence makes the demonstration even stronger. A real physical effect becomes far more convincing when it changes in a precise, predictable pattern, instead of merely sort of happening. Smithsonian Magazine explains that at the North Pole, the pendulum's swing path would shift through a full 360 degrees in 24 hours, while at the equator, there would be no such apparent rotation at all. In Paris, where Foucault made his famous public demonstration at the Panthéon, the predicted shift was about 11.25 degrees per hour, or about 270 degrees in a day. And that is what observers saw. This is exactly the kind of evidence science values most, not just a dramatic phenomenon, but a phenomenon whose rate changes in a mathematically ordered way with location on Earth. A good way to picture the pendulum is to imagine drawing a straight line on a spinning record while your hand tries to keep pointing in the same direction. To someone standing on the record, the line would seem to twist around over time, not because your hand kept changing direction relative to the room, but because the room itself kept turning beneath the line. That is very close to what the Foucault pendulum makes visible. It takes the huge, slow, hard-to-feel rotation of Earth and converts it into a small, patient, measurable change in orientation that can be watched by anyone willing to stand and look long enough. It is one of the reasons the pendulum has remained such a powerful educational instrument for more than a century and a half. Foucault's original achievement in 1851 was celebrated precisely because it offered simple, direct evidence of Earth's rotation. The Coriolis effect provides a second class of evidence, not from a swinging weight in a building, but from the behavior of air and water on a rotating planet. Because Earth rotates on its axis, circulating air is deflected toward the right in the northern hemisphere and toward the left in the southern hemisphere. If Earth did not rotate, the atmosphere would circulate in a much simpler back and forth pattern between equator and poles. Instead, the paths curve. That curvature is not a decorative side effect. It is one of the fingerprints of a rotating Earth. This matters because winds do not move across a still platform. They move across a rotating sphere, where different latitudes already have different eastward speeds. The cause is that different parts of Earth move at different speeds. A parcel of air traveling long distances keeps part of its original momentum, while the ground beneath it belongs to a latitude with a different rotational speed. The result is an apparent curve relative to Earth's surface. On weather maps, this is no small detail. It shapes trade winds, large storm motions, and the paths of major circulation systems. If Earth did not rotate, those structures would not look the way they do. Imagine trying to roll a ball straight across a spinning carousel. To someone standing outside, the ball may follow a straightforward path, but to someone riding the carousel, the path appears curved because the floor itself is turning during the ball's motion. The Coriolis effect is related to that kind of geometry. It is not that air chooses to bend for no reason. It is that motion is being observed within a rotating frame. Noah's Ocean tutorial says directly that instead of moving in a straight pattern, circulating air deflects because Earth rotates. The same rotational influence helps organize large-scale ocean currents as well. This is one reason the Coriolis effect is much more useful at large scales than in small everyday ones. In a sink or toilet, tiny asymmetries in container shape, water entry, and local turbulence dominate, which is why the common household myth is so weak. But in the atmosphere and ocean, where distances are vast and motion persists over long times, Earth's rotation becomes important enough to bend trajectories in systematic ways. Noah's jet stream material connects this directly to global circulation, explaining that Earth's rotation results in an easterly movement influence called the Coriolis effect and helps produce the structure of major wind systems. This is why meteorology treats Earth's rotation as a central physical condition, not a background trivia fact. Once the pendulum and the Coriolis effect are placed side by side, they strengthen each other. The pendulum is a local mechanical demonstration in one place, often indoors, often in a museum or public building. The Coriolis effect is a planetary scale consequence showing up in winds, currents, and weather systems across the globe. One is compact and controlled. The other is immense and environmental. Yet both point to the same conclusion. Earth is rotating. That agreement matters. Science becomes especially persuasive when evidence appears in very different settings and still converges on one explanation. A long pendulum in a hall and the path of air across oceans are not copies of one another. They are different systems responding to the same rotating planet. The body is optimized for footing, balance, and immediate survival. It is not an observatory. A pendulum, by contrast, can integrate slow changes over hours. The atmosphere can reveal rotational effects across thousands of kilometers. In both cases, nature is leaving traces that are too broad or too patient for ordinary sensation to catch. This is why evidence had to replace impression in the history of astronomy. Earth did not begin moving only after humans built better instruments. Humans only became able to see the motion more clearly when they learned what kinds of systems would record it. Even the pattern of what should happen where becomes part of the proof. At the poles, the Foucault pendulum's apparent precession is fastest. At the equator, it disappears. In the northern hemisphere, Coriolis deflection is to the right. In the southern hemisphere, it is to the left. These are not vague, after-the-fact claims. They are structured predictions tied to a rotating Earth, and the world matches them. That is why the evidence does more than decorate a theory. It tests it. A claim about Earth's motion that produces correct latitude-dependent and hemisphere-dependent outcomes is far stronger than a claim based only on how the ground feels. What proves Earth is moving is not a single dramatic image, but the same physical pattern appearing again and again in different places. A pendulum keeps swinging while the floor slowly turns beneath it. Winds and ocean currents bend in opposite directions in the two hemispheres. Large circulation systems take the shapes they do because Earth rotates. Our senses may not register that motion because they were not built to detect smooth, shared movement, but the evidence keeps returning to the same result. It repeats, it accumulates, and it agrees with itself. Once that is clear, the deeper issue is no longer whether Earth moves, but what it really means for anything to be still when every motion is measured relative to something else. By the time all the earlier pieces are placed together, the first feeling of stillness begins to change shape. The floor still feels firm. A room still feels steady. A chair still seems to remain exactly where it is. But the meaning of that steadiness is no longer as simple as it first appeared. The deeper lesson is that rest is never just rest by itself. It only makes sense relative to something else. A glass on a table is at rest relative to the table. The table is at rest relative to the floor. The floor is at rest relative to the house. The house is at rest relative to the patch of earth beneath it. That chain works perfectly well for ordinary life. It is enough for walking, sitting, pouring water, opening a door, or falling asleep in bed. But the moment the frame becomes wider, the picture changes. The house is not at rest relative to Earth's axis. Earth is not at rest relative to the sun. The sun is not at rest relative to the center of the Milky Way. So the calm feeling we call stillness is not false. It is local. It belongs to one scale, not to every scale at once. That is why daily experience can feel so convincing while still remaining incomplete. Human life happens at the scale of rooms, roads, trees, weather, and bodies. At that scale, nearby things usually keep their positions relative to one another well enough that the world feels stable. A cup does not slide off the table just because Earth rotates. A person does not feel dragged across the floor just because Earth orbits the sun. A passenger can sit quietly on a moving train and feel ordinary because the seat, the walls, the air inside the car, and the passenger are all moving together. The train example matters because it strips the idea down to something familiar. Inside the train, local life stays coherent. Outside the train, the whole carriage is moving. Both descriptions are correct because each belongs to a different frame. That is the heart of the matter. Motion is always measured relative to a chosen frame of reference. Once that idea settles into place, the old demand for one final, universal kind of stillness becomes much harder to defend. A person standing in a field may feel motionless relative to the grass, the soil, and the air nearby. But that same person is moving relative to Earth's axis, moving relative to the Sun, and moving relative to the galaxy. None of those descriptions cancels the others. They simply answer different versions of the same problem. Toss a coin straight up inside a smoothly moving bus. To the person inside, the coin rises and falls almost vertically. To someone watching from the sidewalk, the coin follows an arc because it keeps the forward motion of the bus while it moves upward and downward. The coin has not become confused. The observers have chosen different frames. The same event can therefore look simple in one frame and more complicated in another. Earth works the same way. In the local frame of daily life, things behave as though the world is standing still. In wider frames, the same quiet room is part of several overlapping motions at once. That is why the body itself could never settle this problem on its own. The body is built to manage footing, balance, posture, and nearby change. It is very good at telling you that a step is uneven, a car is braking, or your head has turned too quickly. But the body does not carry an instrument for detecting absolute cosmic speed, because physics does not hand us an absolute cosmic speed in that simple form. What the body reads best is change relative to its local surroundings. If those surroundings move together in a stable way, the result feels calm. That calm can be perfectly real and still tell us almost nothing about the wider structure beyond the local frame. Seen this way, the title of the whole video changes its meaning. At first, it sounds like a problem about sensation. Why do we not feel Earth moving? By the end, it turns into a problem about comparison. Moving relative to what? Still relative to what? Once those words are asked carefully, the mystery begins to ease. Earth does not need to feel as though it is racing through space in order to be doing exactly that. A room can feel steady because every nearby object shares the same broad motion. That shared motion is what hides the larger truth from ordinary sensation. There is something almost mathematical about the way local calm is created. When many nearby things move together, their shared motion disappears from ordinary experience. This is why a child can sleep in a plane at cruising altitude. It is why a passenger can read in a train. It is why daily life on Earth seems so stable. Shared motion removes contrast. And without contrast, the senses have very little to report. The eye notices relative movement. The body notices changing movement. If the whole nearby world moves as one, the result feels like rest. That does not reduce the value of everyday stillness. It actually explains why daily life is so reliable. The local frame is not an illusion in the crude sense. It is a working reality. It is the frame in which the cup stays on the desk, the road supports the car, and the body remains upright on the ground. Problems only begin when that practical local frame is mistaken for the final frame of the universe. Then the ordinary feeling of steadiness gets promoted into a claim that nothing larger is happening. Science became powerful because it refused to make that leap. It kept asking what the wider frame would reveal. And the wider frame reveals a great deal. The Earth beneath the house rotates. The Earth carrying the oceans orbits the Sun. The Sun, with all its planets, follows a path through the Milky Way. The Milky Way itself is not sealed off from larger motions beyond it. Once that scale is allowed back into the picture, stillness becomes less like a universal condition and more like a local convenience. It is something we experience when the chosen frame is narrow enough and coherent enough for nearby life to remain orderly. That is why the phrase "truly still" is difficult in physics. In ordinary speech, it sounds simple. In practice, it depends completely on the frame being used. A book can be truly still on a shelf if the comparison is the shelf. It cannot be truly still relative to the rotating earth beneath the house. It cannot be truly still relative to the sun. It cannot be truly still relative to the galaxy. So the word truly does not remove the need for a frame. It hides it. Physics does not let that hidden assumption stay hidden for long. There is also a quiet comfort in that. Once the first discomfort passes, it means the world of daily life is not being taken away. The table is still steady enough to lean on. The bed is still steady enough to sleep in. The body is still right to trust local balance and local stability. Nothing useful is lost. What changes is only the scale of understanding. The room remains calm, but now that calm is seen as something more subtle. It is not the calm of a universe standing still. It is the calm of a local frame holding together inside a much larger motion. A person sitting alone at night can therefore be inside two truths at once. Relative to the room, almost nothing is moving. Relative to Earth's axis, everything in the room is moving. Relative to the sun, everything is moving faster. Relative to the galaxy, faster still. None of this makes the room less real. It only makes the room more impressive. Local order survives inside planetary motion, orbital motion, and galactic motion all at once. The ordinary life we take for granted exists not because the universe has provided an unmoving stage, but because shared motion can be so complete that local stability remains intact. What feels still to us is often not the absence of motion, but motion shared so completely that it no longer stands out. The silence of our senses is not proof that nothing is happening. It is often proof that everything nearby is happening together. Once that idea becomes familiar, the original paradox stops feeling like a contradiction. Earth feels still because stillness in human life is usually a relationship among nearby things. It was never a guarantee of cosmic rest. So is anything ever truly still? In the local, practical sense, yes. A cup on a table is still. A person in a chair is still. A house on the ground is still. In the wider physical sense, stillness only has meaning inside a chosen frame, and every wider frame reveals another layer of motion. The final answer is therefore not a simple yes or no. It is that rest is real where it is defined, useful where it is measured, and incomplete the moment the frame expands. And that leaves the whole journey in a calmer form than it began. The strange part is no longer that Earth moves while we fail to feel it. The strange part is that shared motion can produce such a stable world for us to live inside. A quiet afternoon on Earth is not the opposite of motion. It is one small, stable pocket within it. Thank you for staying with me all the way to the end. I truly appreciate your time, your attention, and the care you bring when you listen to these long science stories. If this video brought you a little peace, or helped make the physics feel clearer and closer, a like or a soft tap on subscribe would mean a great deal to me and encourage me to keep making more. If you'd like, I'd also love to know where you are listening from, or what time of day or night you found this video. Your thoughts and suggestions always matter, and they help me make each next one better. I hope you rest well, and I hope the hours ahead are kind to you.